Continues the topic of relational design, talking specifically about multivalued dependencies and fourth normal form. I know I've reminded you many times about relational design by decomposition, so let me do it very quickly. The designer specifies mega relations with all of the information they want to store and properties of the data. The system decomposes the mega relations into smaller relations that have good properties, no anomalies and no lost information. When we have functional dependencies as our properties of the data, we get Boyce-Codd normal form, and then when we add to the functional dependencies multivalued dependencies, we get fourth normal form. And the specification of multivalued dependencies and the decomposition into fourth normal form is the topic of this video. As a reminder from earlier, fourth normal form is stronger than Boyce-Codd normal form. So if we have here all of the relations that are in Boyce-Codd normal form, some subset of those are also in fourth normal form. When we have functional dependencies, we can guarantee Boyce-Codd normal form, and then when we add multivalued dependencies, that's what allows us to narrow down to the stronger property of fourth normal form. So let's start with an example. We have information about students applying to colleges. The student is identified by the Social Security number. They may apply to several colleges, and in this video we're not going to have college states, just college names. We'll assume they're unique. And then the student may have hobbies. And they may apply, as I said, to several colleges and have several hobbies, but let's assume for now those are independent. So do we have any functional dependencies for this relation? Actually, we don't have any at all. The Social Security number does not determine the college name or the hobby or anything in the other direction. With no functional dependencies, the only key for the relation then is all attributes of the relation. So is this relation in Boyce-Codd normal form? As you might remember from the previous video, Boyce-Codd normal form says all functional dependencies have a key on the left-hand side. Well, since we have no functional dependencies, then the answer is yes. It is in Boyce-Codd normal form. On the other hand, do we think this is a good design? I'm going to say no, this is not a good design. Why not? Well, let's suppose that somebody applies to 5 colleges and they have, say, 6 hobbies. Then to have all combinations of colleges and hobbies, that would yield 30 tuples in the relation, and clearly that's not a good idea. We'd rather separate the colleges and hobbies if they are independent. So the separation of independent facts is what fourth normal form is about. And now let's get a little bit more formal. Like functional dependencies, multivalued dependencies are specified based on knowledge of the real-world constraints on the data being captured, and all instances of a relation with a multivalued dependency must adhere to the dependency. Now let's define exactly what a multivalued dependency is. For a relation R, we write a multivalued dependency using a double-headed arrow, and we say A multi determines B, in this case, again, with A and B possibly being sets of attributes. So that would be A1 through AN and B1 through BM, which I'm abbreviating with A bar and B bar. So now let me write the formal definition of A multi determines B, again using first order logic, similarly to what we did with functional dependencies, but this one's a bit more complicated. It says for all tuples T and U that are in relation R, if T with the attributes A of T equal U for the attributes A of U, again, these are lists of attributes, so if the two tuples agree on their A values, then, and remember for functional dependencies it was simple, we just said they agreed on their B values, but now it gets more complicated. We're going to say that there exists a third tuple V in R that has the following properties. V has the same A values as T and U, so V sub A equals T sub A. Furthermore, V has its B value, okay, drawn from T, so it's equal there. And finally, it has its rest, so those are all the attributes other than A and B, equal to U rest. Okay, so that's a mouthful, but let's look at that pictorially. So here's our relation R, and we'll have the set of attributes A, the set of attributes B, and the rest of the attributes. And now let's make some tuples. So let's say that this is tuple T and this is tuple U. And we said that T and U agree on their A values. So they have the same A values, and then they don't have to have the same B values. So we'll call the first one B1 and the second one B2. And then for the rest, we'll call this R1 and R2. So what the multivalued dependency says is that we have a third tuple, V, and V again has the same A, and it has its B value from tuple T. So it has B1, but it has its rest value from tuple u. So then it has R2 here. So again, what we're saying is that if we have these first two tuples, t and u, then we also have tuple v. Now let me do something a little tricky. Let me swap the roles of t and u and show that we also, with this definition, are guaranteed to have a fourth tuple, and we'll call that fourth tuple w. By swapping the roles of t and u, w has again the same a value. Now it will take its b value from u, and that will give us b2, and we'll take its rest value from t, and that gives us r1. So what we can see here is that when we have the first two tuples that have this particular combination of b values and rest values, it tells us that we must have the other combinations as well. We must have b1 with r2 and b2 with r1. What it's really saying is those b values and the rest values are independent of each other and will have all combinations. So that might get you thinking back to our colleges and hobbies. Incidentally, sometimes multi-valued dependencies are called tuple-generating dependencies, and that's because the definition is about having additional tuples when you have some existing tuples, unlike functional dependencies, which just talk about the relationships among existing tuples. So let's go back to our example. Now we have students applying to colleges and having hobbies, and those are independent facts about the student. So we'll write our multi-valued dependency as Social Security number multi-determined CName, and now let's use some example data to see our definition and how it works here. So here's our apply relation with the Social Security number, the college name, and the hobby. And let's suppose that we have a student 123 who's applied to Stanford and plays the trumpet. And now let's suppose that same student 123 has applied to Berkeley and plays tennis. So what our multi-valued dependency says, and let's make this tuple t and tuple u, is that there's a further tuple v. V takes the same Social Security number, and it takes the first value for the college name and the second for the hobby. So it says that if we have a 123 playing a trumpet at Stanford and tennis at Berkeley, then that same person will be playing tennis at Stanford. And furthermore, I showed that the same definition will generate automatically a fourth tuple with the other combination, which would be Berkeley and trumpet. By the way, one thing you might notice here is that we also have the multi-valued dependency Social Security number multi-determines hobby. This is actually one of the rules for multi-valued dependencies, saying that when you have A determines B, then A multi-determines B, then you also have A multi-determines rest. And we'll see some rules for multi-valued dependencies later. Let's look quickly at a modification of our example where the real-world assumptions about the data are different. So we still have exactly the same relation with the same attributes, but let's suppose that we don't want to reveal every hobby to every college. Maybe we'll decide that we don't want Stanford to know that we're a surfer or Berkeley to know that we're on the speech and debate team. So if that's the case, then what multi-valued dependencies do we have in this relation? We actually have none. And we don't have any functional dependencies either, by the way. And is this a good design? Well, actually, I would argue yes. In this case, this design is a good one because we're not going to have that multiplicative effect of information. Every tuple that we have in the apply relation will be an independent piece of important information. Let's look at one more example before we go on to talk about properties of multi-valued dependencies. I've extended the apply relation now to not only include colleges and hobbies, but also the date of application to a college and the major or majors that are being applied for. Let's continue to assume that hobbies are revealed to colleges selectively, so we don't need to have the same hobbies for each college that a student applies to. Secondly, let's assume that we restrict students to apply only once to each college. But what I mean by that is just on one day. A student can still apply to multiple majors at a single college and to different majors at different colleges. Let's also assume that majors are independent of hobbies, which seems to make sense. It takes some thinking to come up with the right functional and multi-valued dependencies to capture these constraints, but here they are. The first one, when we say that we reveal hobbies to colleges selectively, is actually the absence of a multi-valued dependency on hobbies and colleges. The second one says we apply once to each college, or on one particular day to each college. So that would say that when we have a particular student and a particular college, that's always going to have the same date. So any two tuples for a student and college combination will be on the same date. The last dependency that we'll have involves the independence of the majors that are being applied for and the hobbies that a student has. And so we'll write that as the multi-valued dependency, social security number plus college name plus date, multi-determines major. And remember what that's saying is that major for a given student, college, and date, the majors that they apply for are independent of what we call the rest, which in this case is the hobbies. So you might take some time to look at the formal definitions of functional dependencies and multi-valued dependencies and maybe write out some sample data to convince yourself that these are the dependencies that are capturing the assumptions that we make about the real world. Like with functional dependencies, we have a notion of trivial dependencies, those that always hold, and we also have some rules for multi-valued dependencies. The definition for a trivial multi-valued dependency, A multi-determines B, is in this case that either B is a subset of A or A union B are all attributes. A multi-valued dependency is non-trivial if that's not the case. So let's take a look at why these multi-valued dependencies are trivial. So let's start with the first case where we have our attributes A and the rest, and then attributes B are a subset of A. So let's say that these are attributes B. So what our definition of multi-valued dependencies says is that when we have the same values for A in two tuples, so here A and A, then we have every combination of the B values and the rest. Well, obviously we do, since the B's are subsets of the A's here, the B values are going to be the same as well, and we clearly have every combination. For the other case of trivial multi-valued dependencies, we have A and B together being all attributes of the relation. So in that case, there's no rest. So clearly, we have every combination of values of A and B and rest because there's no rest to combine with. Like with functional dependencies, there are a whole bunch of rules that hold for multi-valued dependencies, and we'll just talk about three of them. And the first one is the most important and interesting, and that's the rule that says if we have a functional dependency from A to B, then we also have a multi-valued dependency from A to B. And I'm going to go ahead and prove that rule for you, again, because this is an important one. I'm going to do this proof using a template for the relation similar to what I did with rules for functional dependencies. So let's say we have our A attributes, our B attributes, and our rest. And what we need to prove the multi-valued dependency is when there are tuples T and U with a certain form, there exists a tuple V of another form. So let's fill in some values first for the tuples. So let's say that we have A and A here. That's what we need for the equality of the A values. Then we have B1 and R1, and we have B2 and R2. And in order to prove this multi-valued dependency, I need to prove that there exists a tuple V that has the same A value, that it has B1 from tuple T and R2 from tuple U. And what I have in order to prove that is the fact that we have a functional dependency from A to B. Because we have the functional dependency, and because T and U have the same A values, what that tells us is that B1 equals B2 here. And so if B1 equals B2, then we know that this value B1 here is equivalent to B2, and in order to prove the existence of this tuple, well, we have that tuple here already, and we're done. So you might check that again, but what that says is using the knowledge of a functional dependency, we can prove that we always have a corresponding multi-valued dependency. Here are a couple more rules for multi-valued dependencies that you can prove for yourself if you're so inclined. The first one is the intersection rule. It says that if we have A multi-determines B and A multi-determines C, then we have A multi-determines B intersects C. The transitive rule is slightly different from exact transitivity. What it says is if we have A multi-determines B and we have B multi-determines C, then we have A multi-determines not C exactly, but C minus B. And you might work some examples to convince yourself why we don't have just A multi-determines C and we have to subtract the attributes for B, although it's fairly complicated. So again, these